So let's talk about domain number 3, security engineering, or engineering and management of our security. Now we have quite a few key areas in here. Some of them are a little bigger than others. We're going to talk about implement and manage an engineering lifecycle using security design principles, fundamental concepts of our security models, which you're probably familiar with already, the controls and countermeasures based upon information systems and security standards, security capabilities of information systems. We're going to look at assessing and mitigating the vulnerabilities of security architectures, designs, and solution elements, the vulnerabilities in some web-based systems, vulnerabilities in our mobile systems, vulnerabilities in embedded devices and cyber-physical systems, cryptography, which that's always got to be there, right? Apply security principles to site and facility design, and then finally wrap it up with some facility security, that physical security. So let's talk about that first one. Implement and manage an engineering lifecycle using security design principles. Now that sounds like a mouthful, and it really is. So doing my research, what I looked for was the International Council on Systems Engineering, since these guys are supposed to be the people, right? Or an SME when it comes to systems engineering. And what they say is systems engineering is an interdisciplinary approach and a means to enable the realization of successful systems. It focuses on defining customer needs and required functionality early in the development cycle, documenting out the requirements, then proceeding with design synthesis and system validation while considering the complete problem. So they say we're going to look at a problem, come up with a solution and a design, implement it, test it, and then finalize it at the end. So that's pretty much what we're talking about when it comes to implementing, managing an engineering lifecycle. Now, there are some steps that you can go through, like concept of operation. Find out what it is that you need. What's the concept of why we're doing this in the first place? Look for any requirements. Say, okay, well, I have this idea, but what requirements do we need to fulfill? Why are we doing this in the first place? What is it that we're trying to accomplish? What is it that we need to make this concept a reality? What kind of budget do we need? What kind of resources? What kind of employees or personnel do we need? What about equipment? What about applications? There's lots of requirements that you have to keep in mind when it comes to these design principles. And again, we're trying to keep security in mind. So you may have to think of encryption systems. What type of cryptography you're going to use in order to make this happen the most secure way. After you get all your requirements, you're going to run into the design phase. All right, so we're going to start taking our concept and start designing it. Right? We moving it, making it mold it, making it look more like what it is that we're trying to get to. Now, through the design phase, you could run into some issues, right? You might have to go back to your requirements. You may start jumping into the design, and you're going to realize something more or additional to the concept that you had. So you may have to go back and get more resources. But once we have it all designed out, because we need a good plan. You always have to have a good plan. Anything you do in IT, you have to have a good plan, right? You have to have that foundation. It's like building a house. You don't want to just put the walls up without a good foundation. We don't want to just jump into some design without a good foundation, without a good design. So once we get it designed out, we're going to start with our implementation. Say, hey, we got it. We're good to go. Let's try to implement this, right? And we're going to implement it maybe in a test environment, some type of development environment. We don't necessarily want to throw it out into production. I mean, if our design was not as solid as we think, and we throw it out on the production network or a production system, we may have some bad stuff happen, unforeseen things that we didn't take into account. And it's just not going to be a good thing. I've seen it happen firsthand. I've seen people take designs and put them right on production because they're come on, we gotta have this, and then it gets pushed out, And it doesn't matter if it's a software, it doesn't matter if it's a piece of hardware that may not have been ready to go. It just did not talk well with the network, and it had vulnerabilities, and it was just a problem. So we don't want to introduce those vulnerabilities, those problems, into our infrastructure, into our network or our system design. So production system, some type of test environment is what we want, not the production system. So once we implement it, we're going to test it and verify it. We're going to run it through the ringer, if you will, right? What is it that we tried to do? What was our concept? We designed that to meet our concept. We implemented it. Now we're going to test it, right? We're going to hammer down on it. You know, you could put it under stress tests. You know, if it's an application, you can do fuzzing tests. You can do vulnerability tests. You can do penetration tests. You know, we want to verify that we're good to go. And then once we verify it, we can validate and say, yes, you know, we did it. Good job. We've gone through the process of this design principles for our engineering life cycle. So we've validated this now. We're good to go. We say we're giving it the thumbs up for the rest of the infrastructure. So we can go ahead and roll it out, right? Put it into production. Put it out there to the masses or inside our organization. And feel good about that. Feel like, it is secure. It's been tested. It's been proven. So, again, it's validated. Now, it doesn't stop there. Just like everything in IT, we have that continuous improvement, right? So we stick our new design inside of our organization or on our infrastructure. We're going to have to do operation and maintenance. Monitor it. Make sure everything's cool. We'll have to update it probably later. We might have to patch it. If we design something for a particular piece of hardware or to work with a particular piece of hardware, what if that hardware goes bad and we have to get something different? Or what if we design an application that's sitting on a particular operating system and that operating system becomes updated? Will our application still work with that? Is it going to have any design flaws now, more vulnerabilities or weaknesses or more risk? So we'd have to go through operation and maintenance, maintain this design that we've created. Now, if you look at NIST, right, our international standards folks out there, they have a 5-cycle planning phase: initiation, development and acquisition, implementation, operation and maintenance, and then disposal. So let's take a look at these. Initiation. So during this phase, the need for a system is expressed. So, the concept, we need something right here, and the purpose of the system is going to be documented out. Not just somebody's going to come up and, hey, I think we need this. Okay, let's run with it. It needs to be a documented process, a formal request, if you will, of what needs to be done. What type of system do we need? So then once we have the request come through, then we get into the development and acquisition stage. Now, during this phase, the system can be designed, purchased, programmed, developed. Somehow it's put together. It's constructed somehow, right? Because that's the whole engineering part of it. So we need to determine security requirements at this point. Right? We're going to look and say, well, what requirements do we have when it comes to security? And that's what I mentioned earlier with those other steps. We're talking about incorporating security requirements into specifications and then go ahead and obtain the system. So we're going to look at our requirements for what we need in our organization, our infrastructure, what policies we have, and determine security requirements and go ahead and bring this in or develop it ourselves, but somehow we're going to obtain this system. And then implementation. Here the system is tested, installed, or fielded, put it out into the field inside our infrastructure. So now we're going to install, tune it maybe, tuning on the controls a little bit, security testing, certifying that it's okay, and give it our stamp of approval, that accreditation that we feel like everything is okay with this system. Then they talk about operation and maintenance, just like we talked about just a minute ago. Here, the system performs its work, so it's doing what it's supposed to do, the operation part. Now, it could be getting modified by the addition of hardware, software, numerous other things that could happen, like any dependencies that it may have. So we're going to be doing security operations and administration, operational assurance. Is it operating the way it's supposed to? We'll be doing audits and monitoring to make sure we're having eyes on the system. We want to have that accountability for any personnel that may be interacting with the system. But again, we're looking at the maintenance and the operations of the system to make sure everything's going the way it's supposed to go. And then disposal. Now, we didn't have this one in the other phases we talked about, but NIST has it in them, in their phases. So this is talking about the IT system lifecycle. This is the getting rid, the disposal, waste, whatever you want to call it, of information, hardware, or the software. So we're moving, we're archiving, discarding, or destroying information, and hopefully we're sanitizing that media. Remember, we talked about degaussing, right? Where we can put that magnetic strip on there or and pull all the electronic fields off of that, say, that hard drive. So that's one way we could sanitize the media. So that's the NIST 5-cycle planning phases when it comes to engineering design. Now let's move on to the fundamental concepts of our security models. And these are probably familiar, or you should be familiar with these. So we're not going to jump way down deep in them, but I still want to hit on them to make sure that we know what's going on here. So we're going to talk about the Bella Padula or Bella Padula, whichever way you like to say it. I've heard both ways. I think it's actually Bella Padula. I used to work with a gentleman, brilliant guy, that actually met or listened to him speak, and that's how he said he pronounced his own name. So that was good enough for me. The BIBA model, Clark Wilson, Chinese Wall, or Brewer Nash, that you may have heard it mentioned that way as well. So the Bella Padula. This was originally developed for the DoD, the United States Defense Department, or Department of Defense. What Bella Padula does is it focuses on maintaining confidentiality of the objects or the data. The confidentiality is what you need to associate this with. So what that means is we're not allowing, say, individuals, employees, personnel with lower security levels to have access to the objects at a higher level. So that maintains that confidentiality. We can't see, if we're down here at a secret, we're not supposed to be able to get to top secret. All right? Now, they have a couple properties that you've probably heard of before, and if you haven't, these are the ones you need to pay attention to. They've got a simple security property, no read up. All right, so if you're at this level, you cannot read up to the next level. All right, that maintains that confidentiality. So a subject at a specific classification level cannot read an object at a higher classification level. So like I said, with a secret clearance, you can't read up to top secret objects. Now they also have the security property, which means no write down. So you can't write information to a lower level either. So a subject at a higher classification level can't write to lower classification. So subjects who are logged onto a top secret system can't send emails, say, down to a secret system. They don't allow that leakage, that data to leave. All right, it maintains that privacy. So no read up and no write down. All right, that's what you need to associate Bella Padula with. And then we have kind of pretty much the opposite of that. We have the BIBA model. And BIBA is concerned with integrity, the integrity of our data. Now, they have a simple integrity axiom, the no read down. All right, so now we can't read down and we don't write up. Again, just the opposite of Bella Padula. So no read down, a subject at a specific classification level cannot read data at a lower classification level. So that prevents them from accessing information at that lower integrity level. Protects integrity by preventing bad information from moving up from lower integrity levels up to the higher levels. So no read down. We can't see what's down there below us. And no write up. So I can't take what I know and write up to a higher level. So again, the subject at a specific classification level can't write data to a higher classification level. Prevents the passing of information up to the higher levels, that they don't have the clearance to make those changes. So they can't affect the integrity above them. Now that protects it by preventing bad information from moving up to those higher levels. So, BEBA model, no read down, no write up. Then we have the Clark-Wilson model. Now this is a real-world integrity model that protects integrity, and what this does, it requires subjects to access objects through programs instead of directly. Now, because these programs have have specific limitations to what they can do and what they cannot do, this model effectively limits the capabilities of the subject. And that kind of makes sense, right? If I have to use a program to access something, but that program does not have the access, I can't get there because I'm using something that doesn't have access to that. So that kind of makes sense. So this uses two primary concepts to ensure that security policies are going to be enforced with this Clark-Wilson model, and that's well-formed transactions and that separation of duties. Now we also have the Chinese wall, Brewer-Nash. I want to throw this one in here. This is designed to avoid conflicts of interest. That's what you need to associate Chinese wall and Brewer-Nash with. Conflicts of interest by prohibiting one person, like a consultant, from accessing multiple conflict of interest different categories. So maybe if you are, say, an attorney, all right, and you have clients, and you have one client, but maybe your wife works for another client. Well, you can't accept that client now because that is a conflict of interest. So having this Brewer-Nash model in place says, well, I can't do that because that would be a conflict of interest for me. So it prohibits them from taking that case. And that's kind of a decent metaphor for a Chinese wall there. Now we also need to talk about controls and countermeasures based upon information system security standards. So what this means is evaluation methods and criteria are designed to gauge real-world systems, security of systems, and products. Now, some of these we need to be familiar with, and you've probably heard of these before. We're talking things like the common criteria or the Orange Book, the Trusted Computer Systems Evaluation Criteria, ITSEC, the Information Technology Security Evaluation Criteria from the EU there. And then PCI, again, we're going to really hit on that one hard for the credit cards. So the Orange Book, or the Trusted Computer System Evaluation Criteria, TCSEC, you may see it as well. A couple different levels in there that they have that we need to follow. Got them listed backwards here, D to A, from the least protection to the most, if you want to look at it that way. Level D, is minimal protection. So this division describes the TCSEC evaluated systems that don't meet the requirements of the higher divisions. We have C level, that's just discretionary protection. Again, that's at your discretion. DAC, mandatory protection at level B there, or MAC. And then A, we have verified protection. That includes all the requirements of B, plus it has some additional controls in there, and they call it the Orange Book because it is an actually book that's orange, a set of documentations there that define a lot more than what we have here. But again, I just wanted to highlight these because you should already have some experience with this material here on the Orange Book. Also, the TSEC, Information Technology Security Evaluation Criteria. Now, this refers to the Orange Book levels. All right, so they've kind of taken what we've put together and pulled this out a little bit, but it separates some functionality, like how well the systems are actually going to work together. And so it separates that from the assurance. Now, there's two types of assurance in the TSEC, or ITSEC, effectiveness and correctness. Now, assurance correctness ratings range from E0 up to E6. So they have a different classification scale than we do. And then the functionality ratings rate from with an F label, like FC1, FC2, FC3. So they have two different labeling systems, if you want to look at it that way, right? The functionality and the effectiveness. And then the common criteria. Now, this is international common criteria, is an internationally agreed upon standard for describing and testing the security of our IT products, of your design systems. It could be the systems, your infrastructure that you have in your organization. A lot of companies follow this criteria because it really lays out how they need to do things. So it presents a hierarchy of requirements for a range of different classifications, a hierarchy for different systems that we can have out there in our organization, in our infrastructure. Now, within the common criteria, there are seven different levels, ELs, each building upon the previous level. So like, EAL 4 can be expected to meet or at least exceed, well, I should say at least meet, but it could exceed the requirements of products for, say, 1, 2, and 3. So if you're here, you kind of encompass everything below you.